Hello everyone. I'll be talking about the idea approach and technical approach for our problem statement SIH-25173, and our team ID is 7128 and the team name is Science of. So moving on, our idea can be explained in two major parts. We have this MCP client and server architecture, and we have this React agentic LLM. So let's talk first about the MCP servers. So we have an MCP client that we created by ourselves using fast MCP, and then we have three MCP servers. So the first MCP server history decides whether a user query needs history or not. If it does, then it decides whether that history should be contextual or whether it should be the last three history. So in this case, the contextual history means the most k-similar history from the vector database. So we're storing all the histories, all the conversations in a vector database, and then we get the last three similar histories if we need contextual history. So this is what the history MCP server does. Now we'll talk about the ELK MCP server. So our ELK MCP server has a lot of tools. So I'll tell you guys about the ones that we'll mainly be using. So the first tool is that it converts natural language to elastic DSL. So it does so using a fine-tuned LLM. Now in this case, we have fine-tuned our own LLM, which is the Llama 3.2 billion, 3.23 billion parameters model, which we will fine-tune using data. And the second function is list indices function. Now this lists all the indices available in the Elasticsearch. Now the third function is get mappings. Now this gives us the data type and the keys for each and every mapping for a specific mapping given. Yeah. And then for search and ESQL, just search the database for the query. Yeah. They just run the query. Yeah. Get shards, get the shard information for all the specific indices. Yeah. And then we have the third MCP server, which is the visualize MCP server. Now this decides whether we need a chart, a table, a plot, or a graph. And if we do, it decides which graphs or plots to make. And then it creates them. And then it also creates a final summary for the data in text. And then all of this is given to the MCP client. And via the MCP client, the result is given to the user. So this is the whole process of the MCP server and client. Now, I'll tell you guys more about the LLM, yeah, the controller React agent LLM. So over here, our controller React agentic LLM has three main stages. So it has a React loop where it first thinks what to do when given a user query. So first it's given a user query. The user gives it some natural language query. Tell me about all the VPN login attempts yesterday. So it takes the user query. It thinks what to do first. So first it decides I have all of these tools. I have all of this tools and the description, and then it thinks what to do next. I can call these tools, I can do this, I can do that. Then after that, it acts on the thinking. So supposedly, it thinks that it has to first check whether it needs history for that particular user his query. So um, since it needs history, it'll call the history MCP server. Then the history MCP server would return some value to the MCP client, whether it be yes, no, or some other value, contextual history, or last three history, and then that result is given to the observation. Yeah. So this arrow you guys can see. So the MCP client gives it to the observation stage. Now here the MCP tool call result is given to the LLM. Then the LLM gets the tool call result and then it creates some observation. So supposedly it got like no in the history. Then the observation would be got no from history MCP server. Now, I'll call the MCP, so I'll call the ELK server since my query context is complete. So then all of this thinking, acting, and observation is stored in a history, and then that history is given for the next loop. So supposedly in loop one, it thought call history. Then in act, it called history. And then in observation, it got like no. So no result from history. And next stage is to call the ELK server. This is one whole loop. And then all of this text data would be saved in history and given as context for the next loop. So in the next loop, supposedly, it has it has the previous loop history. Then it thinks, okay, I've called history. Now I have to call the ELK server to perform accordingly user queries. So for the first, for the ELK server, first it'll call get indices to get what all indices the user has in the database. And then after that, it'll get field mappings. And then after that, it'll convert natural language to ESQL. And then after that, it'll execute it, and then so on. Then I'll visualize, check whether it needs visualization or not, and then so on the result. And when the loop completes, the it gives the result to the user. So the final result is given to the user directly via the React loop, React agentic LLM loop. Yeah. So this is the whole process. Now for a fine-tuned model, LLM model, we're using Llama 3.2 with 3 billion parameters, which we are fine-tuning by ourselves. And for the React agentic controller loop, LLM, sorry, we are using Cohere Command R plus, Chat Cohere Command R plus, which is a really good LLM. It has 128 context window tokens, 128K tokens context window, which is a really good and really big context window. And we've also tried Mistral 7B, but since due to hardware requirements, we've decided to use Chatco here since it runs faster on our hardware, and since it's hosted on a cloud. Yeah. So after that, we guys can take a look at the front end. So the name of our product or solution is Sentra. So Sentra comes from two words, Sentinel and Central. So since ELK is a central place where all the logs are stored, and Sentinel, that's why we use Central, and Sentinel is something that protects something. And since our main theme is cybersecurity and to detect threats, vulnerabilities, and all, so we've decided to use Sentinel and Central. So that's how we came up with the name Central. Now, this over here is the authentication page. So we created an authentication page since it seemed a bit odd to let anyone visit our website and make changes to our database. And also, this is the main chatbot page. And over here, the user can type in their query, send it, and the LLM would give them the response as follows. Yeah. So this is a very short and simple MCP client server architecture. We just have an MCP client. The user talks to the MCP client via directly or through LLM. And then the MCP server, we have three MCP servers, out of which history and visualize we have created. And ELK MCP server already existed by the Elasticsearch website. So they've already, by the Elasticsearch company, they already created an MCP server for that, which is created in Rust, so it's very fast. Hmm. Now, after that, this is also like kind of a short understanding of React LLM. So what it does is that it loops till there is some end condition. So first it'll think, it'll act, and then it'll observe. It'll observe the result of that action. So it loops till the final ultimate goal is complete, and then the result is given to the user. So yeah, that's it. And in the client, also in the MCP client, we will be using elicitation and sampling. So basically, what elicitation does is that through the client, we can dynamically ask the client for some data. So supposedly, we are using ELK server. The React agentic LLM is calling the ELK server. Now, it can't directly execute the queries since it needs to first connect to the ELK, Elasticsearch database. So to do that, it'll first have to get some credentials for connection. So we can do this dynamically by using elicitation. So elicitation just asks the user to for some question, and it asks them for some data, and then the user can provide it dynamically. So this whole process isn't like in the beginning. It just happens in the middle of the whole flow. Yeah. So this makes the whole process very interactive, and it also makes sure that the user doesn't get bored waiting for the result. And it also provides the illusion that something is happening for the user. So we've also like decided that we'll be using kind of a Claude-like front end, where when Claude calls a tool or a MCP server, it shows on the front end that MCP server is being called, MCP server this is being called, it is calling web search or something like that. So we decided to build more on that, and we'll also be implementing that. So whenever a ELK server is called, on the front end, it'll also show that MCP server, ELK server is being called. And we've also decided to stream tokens. So this would also like create the illusion that the result is coming faster than it that the result is coming faster than it actually is. So we've also decided to use sampling. So sampling is also another process where the client can directly call the LLM and ask it for some data or some result dynamically. So in here in our MCP servers, you guys can see whether like it is like decide whether history is needed or not, decide whether charts or tables is needed or not. So who decides this? So our sampling LLM decides this. So for our sampling also, we'll also use an LLM. So the LLM we would use can be Llama 3.23 billion, which can be easily self-hosted. We've tried it. We self-hosted it on our own PC, and it worked really good. It worked really fast. So that's why we decided to use it. And that is the full flow for the MCP server and client architecture. And you guys can finally see the whole complete flow. So user query comes in to the controller LLM, and then the React loop happens. Loop calls tools. Tools give result. Results go to the observation, and then the whole process is repeated till the result is done. Loop is complete. Result is given to the user back. So that is the whole process. And now I'll pass it on to my friend who will tell you guys more about the fine-tuned LLM.
Fine-tuning is the process of taking a pre-trained large language model and training it further on a smaller task-specific dataset so that it adapts to a domain style or a set of instructions. Instead of training a model from scratch, which requires massive data and resources, fine-tuning allows us to build on top of models' existing knowledge and make it perform better for our specific use case. In our project, we are using a Llama 3.2 model, which has 3 billion parameters. This model provides a strong language foundation while being lightweight enough for fine-tuning on modest hardware. It gives us a good uh, balance between performance and efficiency, making it suitable for our experimentation and deployment without the need for very large infrastructure. For the fine-tuning process, we are using a technique called LoRa, which stands for low rank adaptation. Normally, fine-tuning involves updating all the parameters of the model, which is computationally expensive. LoRa, on the other hand, keeps the original model's weights frozen and adds small trainable adapter layer, which uh, we only train these small adapter, which makes the entire process much faster, uses less memory, and allows us to store and share just the adapter weights rather than the whole model. Fine tuning has several advantages. It allows us to adapt the model to a specific domain, improve accuracy on specific tasks, and even control the style and tone of response. Essentially, it makes the model more relevant, reliable, and aligned with the task we care about. An important part of our approach is that we're not using any pre-collected or real data set. Instead, we are synthesizing our own data by prompting different powerful language models to generate instruction response pairs. This method is useful because collecting large, high-quality datasets manually is expensive and time-consuming. By generating synthetic data, we can create a large and diverse dataset quickly, control its quality through careful prompt design, and avoid privacy issues. The way we do this is simple. We design prompts that reflect the kind of queries we want our model to learn. We feed them into different LLMs, collect their responses, clean them, and structure the data into the required format. Then use that dataset to fine tune our model using LoRa. This approach is cost effective, scalable, and flexible. It allows us to train a model on custom data without needing massive real world data sets, and the result of the model is good.